Okay, we're trying to learn how cluster analysis works. We're using a very simple example. First step here is to calculate the distance between every case or observation. So there's lots of different techniques or methods for calculating distance, depending on a variety of factors, what type of data you have. But we're going to use the most common and simplest form called the Euclidean distance. Now, to help you understand this, we've got a very simple example here. Let's start with some data. So let's proceed here on our slides. So we've got 4 customers and we've measured income. We have one dimension. Income is the dimension. Customers are the cases or observations or samples, whatever you want to call those. So just looking at this data, which customers are similar? Well, we can see that 1 and 4 are the same income. That makes them really easy. 3 is pretty close. 3's got 80,000. That's only 10,000 different. And then 2 is much different. So it's pretty easy to put these into 2 groups, a group of customer 1, 3, and 4, and then another group of just customer 2, which is common. When we're calculating distance, we don't expect all distances, we don't expect there to be an equal number of similar distances among all observations. But we rarely, well, although we do sometimes cluster analyses with just one dimension, we typically have 2 to many dimensions. So let's add children here to the mix. How about now? How would you group these? Well, okay, we've got 2 customers with 3 kids and 2 customers with 0 or 1 child. So you might say there's a difference of 2 between 3 and 1 and only a difference of 1 between these 2 and 0 between these 2. So based on children, I would group it into customers 1 and 2 and then 3 and 4. But we've also got income to consider. So how do we put customers, well, I'm not too sure now. How about if we make it even more complicated? Let's add cars. So we've got people making a lot of money with a range of many cars and no cars, and the person making the least money was somewhere in the middle. It becomes increasingly complicated if I have to consider all dimensions to decide how I'm going to group these, cluster them, or come up with some type of distance score to measure how different they all are. Well, Euclidean distance is a pretty straightforward answer to this. Let's give you an example. So here's first of all, our simple distance measure. We talked about this before. These are the differences between customers 1 versus all of them, 2 versus 3 and 4, 3 versus 4. So I can see here easily, okay, those with the smallest distances should go together, like 1 and 2, and then down here, this is the next smallest distance, 3 and 4. And those with the highest distances should not go together. All right, makes sense. Now here's our example with many. So here's how the formula for Euclidean distance. It's the square root of the difference squared between each, we sum the squared differences of each dimension. So here's our children dimension and our cars dimension. So we've got customer 1 versus 2. So let's start with children. Customer 1 has 3 kids, customer 2 has 3 kids. The difference between those 2 is 0. We square that difference just in case the difference turns out negative. We don't want to deal with negative scores. And then later we account for that by taking the square root of the whole thing to get it back into a similar scale again. But anyway, we square that, which is still 0. And then we're going to add to that the squared difference between number of cars. Customer 1 has 0 cars, customer 2 has 1 car. Difference is -1. Square -1, it's 1. So we have 0 plus 1 is 1. Take the square root of that. Square root of 1 is 1. So customers 1 and 2 still look very similar to each other. And that makes sense. So let's go to the next one, and the next one, and the next. Whoops. There we go. So looking at this, the biggest difference is between customer 1 and 4. All right, that makes sense. 1 is a type of person with lots of kids, no cars. 4 is the one with no kids and relatively more cars, although not the most. But you can see how the Euclidean distance now takes and accounts for each dimension in this formula. So I could add in as many dimensions as I wanted to, or as many features or variables, and just include them here in this formula, 3 minus 3 plus 0 minus 1 plus whatever minus whatever squared, and so on, and take the square root of the whole thing. Now, since I'm teaching Tableau in my class, for those who are interested, Tableau uses Euclidean distance, but without the square root right there. Which, again, relative to each other, it'll still give you the same result, but it's just not square rooted is all. So we have a problem, though. You probably are following along so far, but let me show you what happens when we include two variables of completely different scales. So let's go back to our income example now. We can see that customers 1, 2, and 4 are very similar. Whoops, let me keep going on that. There we go. Whenever we compare 1 to 3, 1 to 4, and 3 to 4, the differences are relatively small compared to customer 2 versus anyone, 60,000, negative 50, negative 60. So let's now take into account, let's calculate Euclidean distance by taking into account income and children. So here's our formula. We've got 90,000 minus 30,000, so 60,000 squared, which is some massive number. But then no difference in kids, so that's plus 0 result. And then we take the square root of all that. That gives us our 60,000. But let's take a look at the next one. Customer 1 versus 3. 90,000 minus 80,000 gives us 10,000 plus 3 kids minus 2 kids, which is 2 squared, which is 4. So we take 10,000 squared, that gigantic number, add to it 4, and then take the square root of all that. All it did was change it 0.0002. So you can see the effect of income is massive compared to the effect of children. And as we go through all these, you can see that play out. In fact, the Euclidean distance, for all intents and purposes, is identical to what we have up here with a very simple distance measure of just income. Because this formula, you can see here, the only difference is a few decimals, and in this case where it was 0 before, it's 9 now, because 3 minus 0 squared is 9. Oh, actually that's wrong. That should be 3. I'll fix that, because we take the square root of all that. Anyway, so how do we fix this problem? That's the next question. Well, it's actually pretty easy. What we need to do is normalize or scale all of our data before we run it through the Euclidean distance measure. So the most common technique for normalization is a z-score, although there's lots of them. Tableau uses what's called a min-max score, which scales everything from a 0 to 1. A z-score is, I think the easiest way is actually just to show you. Let me pull up a chart here from Google Images. So a z-score scales the mean, or the center, of all observations to 0, and fits everything within a few standard deviations of the mean. So as you can see here, it can range up to, well, negative 4-ish realistically to positive 4-ish, but most of the data is going to fit along a bell curve here within negative 2 to positive 2-ish, somewhere around there. So the formula for z-score is pretty straight up simple. We take the value or the observation we're interested in, subtract the mean of all observations, divide that by the standard deviation of all observations. Let me do this in Excel actually really quick. That's probably a nice easy way to understand it here. So come on, pull up Excel. There we go. Here we are. So I've got my Excel table. I'm going to add a totals row here to it. Then let's calculate the average here. Here's our mean for each of these variables. I'm going to copy those means and put them right down here. I'll call this mean and standard deviation. I think I still have those in memory. Let's check and see. I'm going to paste values. Perfect. Now let's change this to the standard deviation. Copy that across. Perfect. Copy that. Paste values. Don't need the total row anymore. Let's get rid of that. Table, total row. Perfect. So let's grab my formula right here. I'm going to call this one Z income, Z children, Z age. All right, this is going to equal then the observation, which is 90,000. Actually, let me stick some parentheses around this. 90,000 minus the mean right here, 725, close parentheses, divided by standard deviation. Now I got those divided by zeros because I forgot to put my dollar signs in to keep it on the rows I want it to stay on. Dollar sign in front of the 6, dollar sign in front of the 7. There we go. So as I go down here, it keeps pulling from the mean and standard deviation right here, but yet it automatically moves the value or the observation as we go along. So let's just copy this over for children and age. Oops, copy all the way. Copy down. Automatically, please. There we go. Okay, here's all of our z-scores. So all of these scores now are on the same scale. So I'm just going to use these ones in my previous example. Let's go back to that now. So here's our z-score we just calculated for customers 1, 2, 3, 4. So now the z-score or normalized values for income and children are represented right here, pulled from that table that we just made in Excel. And now my Euclidean distance is 2.09, 1.38, and so forth, you can see. So the ones that are smaller are more alike. You can see 1 and 3 are very alike. Okay, that makes sense. High income and some kids. And then 3 and 4 are alike. So you can see high income and relatively few kids. But it's not quite as straightforward as it was before with children and cars. So the idea when I'm running a cluster analysis is to choose the variables that are going to give me as much separation as possible. So we'll go back to Tableau, or you may have already viewed it, to see how to decide whether or not to include each variable. But this is just a simple example of Euclidean distance.